Welcome, guys, to this edition of the New York Hug. Here we have Kate and Dave, pretty much about to show you guys some incredible clouds, hydrodynamics with atmospheric effects in Houdini. I've been hosting this for about 4 years and pretty much been using Houdini on and off since it began. But now, welcome to Kate. You can go.
Hi. So I'll just jump over to introduce ourselves. My name is Kate Xagoraris. I currently work as a visual effects artist at Mr. X in Toronto, Canada. I've been using Houdini for just over 3 years, so it's getting close to 4. And I've been in the industry just a bit less than that. I run a popular VFX site for Houdini as well. I'm mostly focused in simulation art, but I have a passion for exploring how scientific theories can be incorporated into visual effects and design. The VFX site is called katexagoraris.com, where I'm attempting to collect scientific information that can be useful to VFX artists in productions. On the side, I have numerous articles on VFX, history, atomic, quantum, and particle physics, as well as notes on biology and marine life. On top of that, I've also started a Discord server for artists who wish to collaborate on science-based projects. The server is called Scientific Design in Houdini.
Great. And hi, everyone. I'm David, and I am currently working as a visual effects artist at Pixamondo in Toronto, Canada. I started learning VFX back in 2016 when I was at Seneca College in Toronto as well. After Seneca, I was working at Soho VFX, and I also did a bit of internship at Side Effects itself. And when I was at Side Effects, I did get to work on, I get to test some of their Houdini ocean tools back in 2016 when they were first coming out. So I did some of the guided ocean layer and the masking displacement stuff. I got into VFX basically when I saw Pacific Rim. I just thought, these big kaijus and robots fighting each other. I was just like, I want to work on that stuff. So that's what I did. I went into it. And when I was at Soho, I got to finally, achieve that dream when I got to work on Tomb Raider.
Cool. So today, we are going to be talking about how to explore abstract atmospheric designs and the science behind it with Houdini, as well as hydrodynamic methods you can use to improve your cloud systems. Quite frequently, you'll see a beautiful cloudscape in a film, maybe with a spaceship descending through the atmosphere, such as in the X-Men franchise, or one of my particular favorite shots, which was in Iron Sky, The Coming Race, which came out a few years ago. It's on Netflix. Highly recommend you check it out just for the clouds, it's also featured here in the backgrounds of the PowerPoint. So often when you see a cloudscape in production, they can range from an incredibly accurate landscape of the sky or fall flat when it comes to showcasing different levels of the atmosphere. So we thought it might be a good idea to go and create a collection of ideas and information you could use when building these shots. But today we are also going to explore the idea of creating a planetary atmosphere in Houdini. Space shots are used a lot when it comes to science fiction films, and incorporating ideas on how atmospheres on other worlds should look in our designs is pretty crucial if we want to keep visual effects unique for film. So, you might have seen these images of Jupiter that got released last year from NASA's Juno spacecraft. These images are some of the clearest ever taken of Jupiter, and they probably have changed a lot of people's minds about what this enormous planet actually looks like. Well, today we are going to try, based around these photos, not exactly, but we're going to aim for it. We're going to try and create a proceduralized setup to build a planetary atmosphere. It won't be as high res, but it will incorporate most of the details in this reference, as well as our own spin on what a planetary atmospheres could and can look like, as well as some pretty awesome hydrodynamic tools, particles, and ideas. One thing we will be unable to mimic, but we will touch on the very end, are the anticyclonic storms on Jupiter's surface, which you can kind of see right here in the image. But I'll flip over to a better image shortly. These storms are very different from the ones here on Earth, but yeah, more on that later. Also, the resolution of our clouds be a bit different because we didn't want our computers to die. For this presentation, we'll be talking about the science of the ideas we use to create our design. I'll be talking about walking you through that, and David will be walking us through his setup. David has done a lot of heavy lifting on his build, so he's going to have some awesome insight into how we approach the simulation. So skimming through these images here, you can see that there's a huge variety of colors, worlds, and dynamics. And based on the turbulent flow of the planet, one of the reasons, and based on the turbulent flow of the planet, you get some really, really cool designs. One of the reasons we really wanted to build these clouds is that these images are already really great VFX reference. Plus, me and Dave have seen them being shared through a lot of Houdini VFX groups. And since Jupiter is such a unique planet, we'll be using it as the main reference for this presentation. And it's been a running joke with me and a few coworkers that I really, really, really like clouds. Back in the day, clouds were the first thing I did tutorials for, wrote articles about, and they were also the first creations I experimented with in Houdini. But I never really got to use them in a VFX production environment. So I thought this would be the best opportunity to once again bug my coworkers and insert them into my cloud insanity. And me and Dave met almost 2 years ago at Soho VFX, and I think he can confirm this is absolutely true.
For sure.
Yeah. So there are many reasons why artists may never get to simulate cloudscapes. One mostly being that when it comes to cloudscapes, the majority of work can be done in comp in the map painting department, as well as layout. For example, it is also easier in production-wise to render in comp and map painting than it takes a longer time to simulate a planet, even longer when you're trying to do it to scale. We'll get into more of that later. But often when you see planets in movies such as Avengers Endgame, they are digital map paintings with a 3D base. However, paintings are great when you want to visualize something far away. They aren't so great if you want to do a big pan through the atmosphere or see clouds move. So today we are going to try and do that and incorporate some scientific ideas and try to be as efficient as possible. So maybe, just maybe, someone can try and use this in their own personal little builds. Simulating and visualizing clouds is probably one of the most underrated things you can do in production. Clouds are always somewhere in the background of a space shot through aircraft chases. They also give a scene a lot of ambience when it comes to the tone of the film. For example, let's say you are working on a shot where some characters are walking through a bog or a marshland at night. You probably want to fill the scene with some fog or some mist rolling off the water. So understanding how these cloud systems work is pretty important. So before we dive headfirst into this demo, we need to understand how we approach this project, the ideas we try to incorporate into the final simulation as well. So be prepared for even more science and some fun facts about planets. We also want to explain this process to you as well, so everyone gets an equal opportunity to learn something about atmospheric design, as well as what you might have to think about when attempting something like this. So before jumping into our simulation, we need to take a good look at Earth's atmosphere. There is a lot of science here on Earth that is also applicable to other planets in our solar system and in interstellar space. It is a great starting point to understand the factors we are going to incorporate. It's also very important to talk about because NASA continuously studies life in environments here on Earth to get a better sense of how life might operate on other worlds. And also for this project, it was way easier for both of us to go sit outside and observe some clouds than stare at references on a computer all day. So here's a quick rundown of the composition of Earth's atmosphere. Earth's atmosphere is about 78% hydrogen and close to 23-22% oxygen. And the remaining 1% is made up of carbon dioxide, neon, and hydrogen. The reason we are alive on Earth is because of that lucky 22%. It spans over 10,000 kilometers into space, has many different layers. These layers behave differently the higher up they are, as the pressure decreases the higher up you go. This pressure pushes the elements of Earth's atmosphere down, and this results in the majority of it being bulked around our planet's surface. This is also important when it comes to clouds, as they also behave differently depending how close to the ground they are. The higher up they are, the less air resistance there is for them to move. The farther down they are, the slower they become. Unless you are dealing with extreme pressures, such as other worlds, cloud velocities may vary. There's also names for the levels of Earth's atmosphere. These names are applicable to other planets as well. They are divided into 5 different layers. The closest layer to the ground is called the troposphere. The next layer is called the stratosphere. This extends for over 50 kilometers. Above that is the mesosphere. This extends for another 85 kilometers. The coldest temperatures of the atmosphere reside in these levels. The thermosphere is next. This boundary extends for over 600 kilometers. And then finally, the uppermost layer is called the exosphere. The pressure of Earth's atmosphere is also known as barometric pressure. It is measured with something called a barometer, and the units of it are measured and labeled as ATM. 1 ATM unit is equivalent to an average atmospheric pressure at sea level. The barometric pressure of Earth is around 1 ATM. So after that information dump, it's also a great idea to take a look at some clouds in and around our planet. These cloud types are also applicable to other planets as well. Clouds are classified according to their height above the ground, depending on which category they are in. They have unique names that correspond with them. There are about 5 different categories of clouds. However, cloud species can change and overlap between these categories. This isn't a complete list of all the different types of clouds, but a few that are very relevant to this presentation. You'll also see that a lot of creativity from the scientific community went into the names of these cloud categories. Extreme level clouds. There are clouds that exist anywhere between 80 to 85 kilometers in the air and in the atmosphere. The species of clouds that exist here are noctilucent clouds, as well as with other wispy forms of stratoform and cirrus clouds. Very high level clouds. These clouds exist anywhere between 18 to 30 kilometers in the atmosphere. These species of cloud exist here are cirrostratus, haze, stratocumuliform clouds. High-level clouds, these are clouds that exist below 13 kilometers to 5. In the atmosphere, the species of clouds here exist are cirrostratus clouds as well. Mid-level clouds exist here between 2 to 7 kilometers. Altocumulus, altostratus, nimbostratus clouds are here. And then low-level clouds are your fog, cumulus clouds, and stratocumulus clouds. So that was a lot. But in these categories are a few interesting bits of clouds. Sorry, I think my pet rabbit just is zooming around his cage. Ignore anything in the background. But I also think it might be fun to talk about these 3 types of clouds, because Jupiter and the planets in the solar system are very much filled with thunderstorms and very high velocity storms. So rain clouds are also known as nimbus clouds. They usually form under 6,500 feet. And just like their name describes, they produce some forms of precipitation. Then we have wall clouds. Wall clouds form directly under thunderstorms. They rotate and have been known to form tornadoes. They do not produce rain, but they are also formed under drafts and gaps in the gaps in these clouds. Shelf clouds is a cloud that forms ahead of a thunderstorm, and they form in a wedge shape, and they are almost spherical. They usually stay on the outside of the storm and line the edges of it. And then we have hole punch clouds. These clouds are also known as fall streak holes. They are usually clouds that have a large gap in them and are circular in shape. So now, after that, we can jump into Houdini. One cool thing to note about clouds, that even though they are volumes, they don't behave like static volumes of regular pyrotechnics. They move a lot like fluids, and because the constant pressure on them from Earth's atmosphere, this fluid-like motion gets extreme based on the altitude of the atmosphere. The study of the behavior can be classified as hydrodynamics. Hydrodynamics is a study of forces acting on or exerted by fluids or gases. Because clouds on Earth are made up of water molecules that alternate between solid, liquid, and gas states, they can fit into the study pretty well. There have been many studies on this field on clouds, and there have been hydrodynamic studies to show how clouds collide with each other and the turbulent flows that surround them. And hydrodynamics is quite possible to replicate in Houdini. The entire fluid system inside the software is completely compatible with smooth particle hydrodynamics and other dynamic fluid simulations. It is also capable of introducing kernel noise and other forms of variables into the fluid simulations. Houdini can also handle various other noise types, such as Perlin and curl noise. Curl noise is especially useful as it is a non-divergent noise type, meaning it can produce fluid-like motion when applied to particles. Noise types are very important in fluid dynamics or hydrodynamics, as introducing different types of noise can be caused by varying amounts of friction or other factors in your simulation or things that you're trying to replicate, depending on what your experiment is about or what materials you're trying to mimic in your simulation. Thinking about materials in a hydrodynamic simulation is important since non-cohesive and cohesive materials will act differently with fluids. Houdini is also pretty agile as it allows you to evact flip simulations in pops with volumes, affect their velocities, and change the viscosity as well, which gives you a whole range of fluids to simulate. This means you have the possibility of basing the movement on fluids and particles off of pyro simulations, which is great if you want to show how gases and fluids behave together. The software can also give you the ability to mix gases in a confined area, which can also be very helpful in the study of hydrodynamics. A lot of scientific simulation and experiments involve the use of pressurizing fluids and gases in tubes or other containers, so I would personally love to see Houdini used as a tool to further develop and visualize scientific experiments in this field, as its flip and fluid tools are probably some of the best out there. One cool little space-related note about footnote is that hydrodynamics have already been used in simulations to simulate galaxy clusters. And another thing I wanted to mention is that smooth particle hydrodynamic simulations were first developed for the astrophysical field. So every time you use the system in Houdini, you're technically qualifying as a space scientist. And NASA does hire people to teach their departments on how to use Houdini. So, clouds and Houdini. Since we're also talking about clouds today, I thought it might be great to talk briefly about the various other ways to build clouds in Houdini that we won't be showcasing in today's presentation. Houdini has some pretty awesome default cloud shelf tools, which I'm pretty sure a lot of artists are already familiar with. The cloud rig tool allows you to automatically drop a rig with a cloud node, cloud noise, and allows you to apply lighting to the clouds. The cloud SOP itself, as well as the cloud noise SOP, are made of proceduralized and subnetted volume VOPs and VBDs, which is great for quick and easy setups. However, if you want to make scientifically accurate clouds or clouds based on winds in the atmosphere, you'll have to take your simulations even further. Since Houdini 17, there's been an amazing node called the point velocity SOP. The SOP can allow us to generate and customize velocity attributes on points, and once rasterized, you can evact pretty much any VBD or volume by them, which is great if you want to quickly create animated clouds or wispiest, curious cloud species. You can even add noise to its velocity, which can be helpful when creating variations in clouds. Volume VOPs are also amazing when it comes to adding further details because you can create density ramps based on the altitude the cloud resides at. You can further manipulate your clouds with velocity trails, pop networks, and flip sims, which is great if you don't want to animate your clouds with volume VOPs, and if you want to create really abstract clouds. But pop sims and fluid flips are something we're going to get into next because they play a huge role in hydrodynamics. So after learning all this, let's take a look at some excellent 3D hydrodynamic and cloud simulations that the VFX community has done, and some very other talented artists have done as well. So I think this is a great time to mention and give a shout out to a great artist in hydrodynamic visual effects. That woman is Nicole Sharp. She runs a site called Fuck Yeah Fluid Dynamics. We'll leave her link to her site up here on the presentation so you can go check it out. She's been running this site for over 10 years, and she collects pretty much everything you need to know about fluid dynamics. So I highly recommend you check out her site if clouds or fluids are your thing. She also has a collection of clouds, and it was a great starting place for me. It gave me a quick and easy logical starting point for our simulation. Her notes on the clouds of Saturn were also quite interesting to us, as it gave us some names for the shear instabilities forming along the edges of its clouds. Shear instability is also known as Kevin-Helmholtz instability, which results in shear stress caused by extreme velocities in fluids. One of the best resources we could have ever asked for this presentation was from a bunch of Pixar papers that were released from Seoul, which were about rendering volumes. These papers and references were great because it allowed us to set a standard of how volumes are rendered in production. There are also a bunch of delightful articles written for level 80 about clouds by a bunch of artists that I would highly recommend every artist in volumetrics check out. I'll try to pronounce their names. Koldrit Bojan, I'm sorry if I pronounced your name incorrectly, has an amazing article on creating realistic clouds in Houdini. And I can say I've personally used it in studios while researching atmospheric effects. Camelia Samani has some amazing articles on a level 80 about the development of her cloud creation for short films. She shares not only her technical background in Houdini, but also her scientific background, which is really cool. And she also describes her ways she approached her effects. Her research for her effects, which took over 2 years, and she was able to create some very realistic results. So, some fun planetary facts as we break away from Earth. In our solar system, there are 8 planets, 5 dwarf planets, and over 200 plus moons. However, 4 of these planets are gas giants, and only one of these moons contains an atmosphere. Gas giants are also described as large planets composed mainly of hydrogen and helium. They're also known as failed stars, which means they are made up of more compressed gases than solid elements. These planetary atmospheres are layered, similarly to Earth's, but are different in their own unique way. They have some of the same names for the levels of their atmosphere we'd give our own. One defining feature of a gas giant is that it has a layer of metallic hydrogen. This hydrogen is referred to as metallic because it is so compressed in the atmosphere that it turns itself into an electrical conductor. But because our one reference is from one particular gas giant today, let's dive into Jupiter. Fun fact about Jupiter, it has only 3 main levels to its atmosphere, and it's thought that Jupiter's rain clouds contain ammonia crystals and ammonium hydrosulfide. We've also carried this 3-layer system into our build we will be showcasing today. Jupiter is a little bit different from Earth, as instead of a mostly oxygen-rich atmosphere, it contains other chemicals and compounds. Because the pressure is so great on the planet's surface, the gases get compressed to an almost liquid-like state, so much that they are forced to compress beyond their critical pressure point. Its atmosphere is very interesting because of its compounded atmospheric pressure. The upper layer consists of about 75% hydrogen, 24% helium, and random elements that can contain the remaining 1%. The lower levels of the atmosphere make up about 71% hydrogen, 24% helium, and 5% other elements. These trace elements are methane, H2O, silicon, and ammonia, as well as carbon, ethane, in both gas and liquid form, hydrogen sulfide, neon, oxygen, and sulfur. When combined together, these elements produce pigments of white, orange, brown, and red and blue. These white clouds are from ammonia crystals, the blue tints are from hydrogen, the orange and light pink are from helium, as well even more blue from the methane crystals in the clouds. Also, an important footnote in the color of Jupiter, because the elements in its atmosphere are ionized, as we discussed from metallic hydrogen, the frequency of the color in it might change. Which is why if you look at any of the more recent pictures of Jupiter, they vary in color a lot. So its pressure is also very important when you're trying to build something similar to a gas giant. So looking at Jupiter's atmosphere, it's a bit different from Earth, but this also has a huge factor on its weather systems. Jupiter has the deepest planetary atmosphere, bigger than any other planet in our solar system. This is because of its massive size. Jupiter is 11 times bigger than Earth and 317 times its mass. The pressure is so extreme on Jupiter that most of the elements in the atmosphere behave like fluids. The pressure also causes extreme temperatures on its surface. The origin of its pressure is caused by the heavy elements contained within it. Hydrogen and helium are so dense that their weight presses down on the planet's core, and this also causes their molecules to slow down and they begin to crowd together. And here they become a liquid and start to swirl. On average, there's about 650 million pounds of pressure pressing down on Jupiter's core. We've been fortunate enough to confirm some cloud types on Jupiter as well. We know for certain from NASA and the ESA that Jupiter does contain wispy bands of curious clouds on all levels of its atmosphere. Wave and haze clouds as well have also been observed in the mid-level layers, and connective clouds on the lowest part of the atmosphere. Connective clouds are clouds that make up thunderstorms. Its cloud cover is about 50 kilometers deep, and the majority of its storm system we can see from satellites are in the tropopause layer. The Great Red Spot, so our storm system, also resides here. So I think it's time we talked about the most famous aspect of a reference, or of Jupiter, and that is the Great Red Spot. The Great Red Spot is the largest and longest active storm currently in Jupiter's atmosphere, and is arguably one of the longest ones in the solar system. It's defined as an anticyclonic storm, which is a storm system that moves in the opposite direction the winds around it are operating in. There's evidence to suggest the storm has been around for over 356 years. However, it's starting to shrink in size, so perhaps someday it will completely disappear. The storm system is filled with detail. It has a unique swirling pattern at its center, and is filled with wave-shaped clouds. Punch-hole clouds have also been observed around the Great Red Spot as well. Based on this color, we can also assume that the storm is made up of clouds containing oxygen, helium, silicon, and neon. But one hypothesis for its color is that the sun's radiation is reacting with the ammonium hydrosulfide in the atmosphere. So the storm might not actually be red at all. It might be a completely different color, or rather an optical illusion. So, I mentioned before, it's a bit challenging to create anticyclonic storms in Houdini. It is possible because tornadoes and hurricanes can be built with the software, and there's a lot of tutorials existing out there showing you how to create them. But the Great Red Spot and other large anticyclonic storms on Jupiter are a bit different. Because of how compressed and dense the atmosphere is, the flow of the storm acts a bit differently than the regular anticyclonic storms here on Earth. It emits huge amounts of gravity waves and acoustic waves from its center, which also have an effect on the clouds around it. Because there is barely any friction due to the lack of surface on Jupiter, the storm has the option to chaotically move wherever it wants to. So predicting and manipulating its design was a bit too difficult for us. And because of that, we would have to base our entire model around this one storm. And that probably would have led into more issues than we bargained for. So we'll leave its future simulation and design up to you. So you might have guessed from how we also described how fluids move on the surface of Jupiter. The overall hydrodynamic flow of the planet is a little bit different from what we'd see on Earth, but they still behave well within Bernoulli's law. Bernoulli's law states that an increase in the speed of fluid occurs simultaneously with a decrease in static pressure or a decrease in the fluid's potential energy. Basically, any fluid that is in a steady motion can be covered by Bernoulli's law, and this law is used a lot within hydrodynamics. It is also important to note that in hydrodynamics, this law is referenced in some different terminology. Science often talk about how flow patterns in fluids and their corresponding streamlines exist. Any flow pattern that is steady may be seen in terms of these set streamlines. These streamlines are trajectories of imaginary particles that's suspended in the fluid and are carried along with it in a steady flow. In a Houdini VFX sense, you can think of these streamlines as markers that show an attribute of motion for the liquid, for example, a velocity attribute or an age attribute. So it's less complicated than it seems. So with that in mind, what type of flow does Jupiter have, or how can this flow pattern be seen on other planets? Jupiter's clouds move in a combination of laminar, common steady, and turbulent flow, or chaotic. These flows are not visible to the naked eye, but the reason you can see these in these high-res photographs is because some very crafty open-source artists have painstakingly stitched together the bands of RGB channels the Juno spacecraft sends back every 53 days, which is why they're so high-res. They're just tons and tons and tons of channels. These flows are also very similar to ones seen on Earth's oceans. Turbulent flows in water are also important for the ecosystem as they move nutrients and other matter around for sea life. So it's quite possible that Jupiter's atmosphere carries this concept. And there's other factors about its atmosphere and overall ecosystem on its planet that we just don't know about yet. So flipping back to this wonderful picture of this planet, we can start to apply this knowledge from the pictures to the planets. And just by looking at the images, we can see some extreme examples of almost every cloud type. They are somewhat harder to see as they're being mixed together by high winds, but there overall seems to be a lot of velocity sharing in the clouds and a lot of turbulence. There seems to be a lot of equatorial wave systems in the images. These are clouds that are trapped along a planet's equator. So you can kind of see these banding lines or lateral bands. These are equatorial wave systems. And they also disappear vertically away from the equator and also crowd around the equator as well. We can also see small amounts of level stratus and curious clouds forming on top of Jupiter's swirls. They're barely visible in this image, but they're kind of like these little tiny dots here. That's what they are. Because of the amount of rotating storms in the atmosphere, we could also assume that most of Jupiter's cloud systems contain wall-like clouds mixed in with a variety of nimbus cloud systems. There's one other factor on gas giants and atmosphere effects we do need to talk about, and that's gas giant rings. Originally, when I looked into this, I didn't think they were part of planetary atmospheres, but they are. When you think of a planet with rings, your first thought might be Saturn. Every gas giant in our solar system has a set of rings that surround it, and these rings can vary in levels of visibility, but are mostly made up of dust, ice, and other small, medium-sized space debris. These rings are often interact with the planet's atmosphere, and the aerodynamic drag from the planetary atmosphere can actually vary the speed of the rings. Because planetary rings form in our solar system, they can also happen on exoplanets. They haven't yet been observed up directly, but are theorized to exist. And when a planet forms, they usually form from a large cloud of matter or rings orbiting a star. So any leftover material would circle the largest gravitational force, which in this case would be a planet or a star. So atmospheric studies also go well beyond our solar system. NASA and other space agencies have observed planets beyond our solar system in the search for extraterrestrial life. An exoplanet is a planet existing beyond our solar system, and the first evidence of exoplanets was in 1917. It has now evolved into a full-time search for researchers across the globe. By observing a planet's atmosphere, we can see if they're a good candidate for supporting life or emitting signs of life. Scientists can do this in many ways. They can use a few mixed methods of transmission, photometry to measure the direct emission or spectra of a planet's surface. By measuring the way the planet reflects light from the surrounding star, scientists can take a good guess on what elements make up its atmosphere. They can even get so far as to detect different cloud types in exoplanets, which I find very interesting because they're millions of astronomical units away. So, after all that, we can now jump into our demo. Here's our best representation and realistic way of building an exoplanet atmosphere and cloud formations in a proceduralized way. Dave has done his best to proceduralize these systems and generate some interesting renders. So here's our own personal flyby and breakdown of the file. We've also tried to incorporate these theories into our final simulations, such as high velocity clouds. So movement will mimic a liquidous movement of pressure pushing down on them. And they will also contain a fair amount of turbulence. We wanted the clouds to be affected by gases, so we've also combined that into the sim. We've tried to mimic turbulent flows seen on gas giants, carry through the colors that would be seen in a typical gas giant, and try to create a build that is efficient as possible and is doable in a VFX production. So I'm going to hand it over to Dave, and Dave's going to show us what he has.
Thank you, Kate. I'll take over here. You rest up for a sec. That was great. Lots of good information. All right. So first, I had to figure out how exactly I was going to approach this. As an artist, a lot of ideas come to my mind, and I'm thinking, how do I make this effect with, do I make it with particles, smoke sims, a combo of both? So what will give me the best or closest results to the look we're trying to achieve? So then I start trying some things out. I originally started with mixing different density fluids. and inside of like its own flip sim, I realized that, I did that because based on the density values that we're aware of with hydrogen and helium elements. Shortly after trying that out, I realized it's not practical for achieving this in a short amount of time and to look good. So I avoided that way of approaching it. So then I also had to figure out, how am I going to achieve this look in a spherical manner so that I represent a planet? Maybe I'm thinking maybe the suction tool in Houdini. It could very well be an option to use for this, but it's not the way I decided to approach it. So to get the swirls you see, I thought I'd try using like a smoke sim to drive a particle simulation to get those nice swirls that you see, that you seem to be familiar with, as in hydrodynamics, liquids that are often affected by velocity fields or other gases. So what I did here, just move that. It just simply moved some spheres, or set some spheres around, and I just kind of like moved them past each other to try and mimic the banding effect that you've seen in those pictures. It's very simple. I'm sure everybody's done this type of source before. Let me see here. Then I moved over to the smoke sims, and I just did something simple. I just added some dissipation, very basic forces. I didn't want to get it too complicated just yet. So after I had a basic smoke sim, which I can show you here, this is what I kind of used to drive the sims for the, a Jupiter attempt. As you can see, I tried to get these nice swirls, slow movements, liquidy movements. So after that, I basically made a fluid tank. And I made what you can see here. It's just a very thin tank. I just wanted to use a small amount of particles so that I can actually realistically do it with my machine. So this tank obviously is only 1.1 meters thick. So in a separate .NET, I imported the tank into a flip object as an initial particle data field over here. And while simming, I decided to I'll show you here. I grabbed this picture of Jupiter, put it on my particles with the attribute from map node, and I just did it for fun, for the sake of testing. And eventually we moved away from this, but it was fun for me while I'm building, which you can see here. This attribute from map node. Sorry. Then I brought so after doing that, I'm sorry here, just losing my losing my placement. So I will grab this. I want to show you guys what I kind of ended up getting. So this is just some experimentation. When I bring in those smoke sources I showed, I imported those sims into the fluid object. The fluid sim. You can see that I'm starting to get these nice swirls and I'm thinking, this is actually pretty good. This is getting pretty close to mimicking those shapes that we've seen. So now, after I start getting these type of patterns, I'm thinking, what can I do to make it better? So I started, I lowered the velocity scale in the flip sim to see, less chaotic motion. I added, these second sources, because originally I just did the one. Obviously, you always got to start small when you do these sims and work your way up to the final product. started adding some turbulence to it, and I added a control field, which you can see here. I did not want the disturbance to be everywhere in the sim, affecting all particles in that box. I just wanted them wherever the smoke sim was, so you can get some more details in that area. And I did that right here. Just control settings, density, just like that. Then I started adding some viscosity to the smoke objects, just to mimic a more slowly moving fluidy effect. And then once back inside the flip sim, I started to play with some parameters. I added viscosity and add some receding for surface oversampling, just to fill in any gaps that might happen as the smoke sims are passing through the box. Another thing I did was to make sure I had a closed boundary. I did not want particles flowing in and out of this box. I just wanted to isolate all the forces inside of this group of particles. My final sims were probably 4 million particles. I didn't go overly large, basically because it's the limit of my machine, but still managed to get some pretty decent results. Let's see here. So just like most of you in production, I too hate waiting for caches to finish or waiting for farm time. So I tried to make this as efficient as I possibly can. So when I had this sim run through the particles here, which I will get a flip book for you. So when I had this running through, I did not want to think about making this into a cloud all at once. I basically just wanted this main area that the sim is happening. So what I had to do was I had to create a mask so that basically this mask can transfer an attribute that can isolate this area. And I made that mask by changing the smoke source, this that you've seen, into a mesh. So I turned it into some polygons, which you can see here. So I just converted the smoke sim into polygons. And then I basically, inside of the fluid DOPNet, I added a SOP solver over here. I imported it, gave it a mask attribute. Sorry, no, very simple. Just did my own little time shifting stuff, nothing out of the ordinary. And then just attribute transferred it. And I can show you that as well, what the result of that is. So you can see here, this is the mesh transferring to the points, the mask attribute. It doesn't really add too much to the sim time. It's fairly quick. Basically, like I said, anything you see that's white is what I kept. I did not want any of this black particles for becoming a cloud later on. Wait up through one more time. All right. So from that, I can show you the post-sim stuff. So basically, I isolate the mask, and oh, you can already kind of see something there. But I started thinking, the spherical shape, I needed to create basically I need to bend the thing. So I created just a simple lattice, bent it backwards, did this all post-sim, because doing this in the actual sim would be more complicated than it is just to do a post-sim. when I realized that we obviously need to keep the colors, like, that we hydrogen, and then they kind of create that orange effect on Jupiter. So I realized, well, we got to keep the colors. It's got to be the best thing to do. So just did a simple VDB from particles. Add some cloud noise for the sake of adding some more details to it. Add a volume so we can keep the color, so basically we have a vector with a color. We use the volume from attribute node, which really is the main thing for keeping the whole color. It's a great node inside of Houdini. And when you merge these two together, you don't immediately get the color. You have to use a volume visualization node. And it's just as simple as just putting CD into the diffuse field. And I will show you that as well. Right up here. So this is the mask. And then just in a second here, you'll see that the final product, using those BDV conversion nodes, you get all the nice swirls from the sim. And I'm basically just keeping this nice area, this nice thin area of particles and cloud. You can see the nice details were kept from the sim. Now for the shader, it was fairly simple. I just need to add a surface color node with point color turned on and attach it to a volume shader core, which I'll show you over here. Oh, yeah. So you can see surface color, point color. This is just my alterations with it. Volume shader core. It just goes into smoke color. Simple as that. This just gives me the extra density values that I want to play with for the final renders. And Kate will have those renders later, but basically we had some issues getting this to be an animated sequence that we really wanted to show you. It was too hard to push it as far as we could and in the amount of time. So I'm thinking we'll probably come back and approach this after the presentation, and sometime in the near future, you should see an animated version of our clouds, basically, or atmosphere, planetary atmosphere. As you can see here, this is the whole setup. I made 3-4 layers because there are 3 to 4 layers on Jupiter. So basically just doing different things inside of each one, different movements of the sources, different velocities. Yeah, I inside the flip sims, like, also had its own viscosity parameters. I just really wanted to try and get that fluidity effect that you see. I know that you could easily add some complicated velocity field instead of using a smoke sim like I did, but it's just not the way that I approached it. Maybe if I did it a second time, I would approach it a different way. But for a first try, I think we ended up getting some pretty good results. Yeah, at the end we decided to add some last minute things, like, maybe like the nice outline you see on Earth, like the blue atmosphere line high up in the atmosphere. We thought, add that as well. Add some clouds, just like very small details right above this fluid sim that I made that you see here. And then we also had like rings. We also built some rings for the planet. It was also like an afterthought, but if anybody has any questions about that, feel free. I'll go through it. I'll get into more details of my build if anybody wants to know. But this is basically the result of the simulation that we're trying to approach. And here's another layer I can try and show just to get some different patterns going. So you can kind of see those liquidy movements, nice swirls. And it also doing it this way also allowed me to make many iterations or make a lot of changes very quickly. It did not have to take too much time. Like a sim like this, probably 15 minutes or so, 15, 20 minutes, didn't take too long. But at least having that quick of a sim allowed us to get to these results quicker than we wanted. So I'm gonna pass it off to Kate again. Like I said, at the end, if anybody has more questions about this, I'm happy to answer them. So yeah, thank you very much. Hope you guys enjoyed the build. And back to you, Kate.
Hey, David, thanks. I will reshare my screen and I will show you some of the end results of our simulation. So these images were a bunch of different results we were able to generate with this build. As you can tell, a lot of different results you can generate with it. And I liked it because it was pretty customizable. I created our different versions of exoplanets. So I guess you might ask, like, why is it oh, shoot, go back. I guess you might ask yourself, like, why is this important? So why should we do sims over map paintings and visual effects? So I've mentioned before, map paintings are usually used when it comes to creating planets for productions, but it doesn't mean they don't have to incorporate science too. But simulations are needed for close-up shots and pan-through simulations, things like that. However, the more realistic you make a simulation, or the more movement it has, the more connection you're going to have with an audience. And when you're dealing with a science fiction shots and films, you need them to be believable. And when you're dealing with fictional adaptations on the big screen, it is very easy to assume how creatures or effects might behave in an alien environment. A lot of films start to fall apart because of the lack of science behind them, and that can also make their plot less believable and less interesting. And by adding the smallest detail to a planet's atmosphere, you can start to brainstorm where and how an alien from that world might behave. You can even start to answer questions about the type of air it breathes or the climate it can adapt to and environments it thrives in. Plus, everything in the movie will match its behavior. So in the end, science can be used to engage an audience as well and further educate anyone who watches the end result. Plus, I think everyone loves a good science visual effects breakdown for a film. I know personally, I love it. So, final thoughts. I mentioned in passing when we were wrapping up this project, to a group of artists who I'm friends with, that I didn't think anticyclonic storms on Jupiter were possible. And based on their structure and proximity, that's where I thought the conversation would end. But that's where one incredibly talented artist proved us wrong. And his name is Jeremy. Jeremy, and I wanted to credit him because he opened our eyes to the idea me and Dave overlooked for this build. So last Tuesday, Jeremy Joswick, I think I'm pronouncing your name right, is a very talented VFX artist who has worked on almost every DC superhero show you can think of, sent me this. And he was able to create several custom volume bops and velocity trail attributes matching of how Jupiter's turbulent storms move, which if you compare it to, if I can switch over to the next slide, to Jupiter's storms, are almost identical. So I think after this presentation is done, and with Jeremy's permission, we're going to include another round of testing with this build and this velocity system, and then generate even better results. And the other thing I wanted to mention this is that science and visual effects is all about collaboration. And this is also why it's so important to have scientific visual effects communities, because without them, I doubt the progression of or improvements to visual effects could be done. Plus, our imagination will be limited by what we can just build in a studio. And I also think it's great to have artists like this working on superhero shows, because that's where the science is needed in visual effects. Abstract thinking is the best way to save a superhero franchise. So, there is also one more thing I wanted to mention, before we wrap up, and that there's a ton of possibilities the Houdini community can do with hydrodynamics. There is a bunch of ideas you could explore with the software and see where it goes. So one of my favorite topics is the cosmic web, and another way to simulate it is through hydrodynamics. There's several articles out there that came out this year where someone was actually to successfully replicate the entire cosmic web through hydrodynamics, which I found fascinating. As I previously mentioned, galaxy clusters are also a big thing when it comes to hydrodynamics. Carbon burning in massive supermassive stars, miscellaneous gas simulations you can also build, and gravitational development of stars. So, after this long presentation, we'd just like to thank the following people, as they were able to give us some awesome references and resources for the science behind this presentation, as well as some general advice, criticism, and help in and outside this project, and also people who have generally supported us as well. Are there any questions?
Yes, I have some questions.
Yep.
So my name is Jerome. I work at the California Academy of Sciences in the visualization studio. So we're actually finishing up on our 8th in-house planetarium production. So from my perspective, it's just pure joy to see you guys do this. I think we need to see more of this kind of scientifically accurate, visualizations. So kudos. So one question I have is, are any of these files available to share for us to study?
Sure, we can make them available. We'll definitely we can also post iterations of them as we go, if that's beneficial to you.
That would be good. Thank you.
I can do it. Didn't even think of that, but yeah, thank you for being interested. I'll definitely prepare that.
Great, thank you.
It's great to talk to you in person. I think we've been talking online a little bit.
Yes, likewise. I'm a huge fan of your
it's great to see you in person.
Likewise, I'm a fan of your work. So
we'll definitely post more things as we go. Again, building something this huge was not a task that we could do overnight. And then just one thing that I'll also add about this build is that during the last week and lead up to this presentation, I was kind of posting little teasers of the build, and it just sparked something, because suddenly, especially in the Discord server that I created, people started posting their own versions of Jupiter, which I found very, very interesting. And it was very interesting to see these people also wanting to collaborate on the same thing. So we'll definitely post our files and pictures as we go along.
Great, thank you. And where would be the best place to coordinate that? Via email or via your website?
I can definitely put it on my website, and I'll also put it in the Discord server. And maybe we can even post it in the meetup group here so people can grab the file as well.
Cool, thank you.
Yeah.
That'll be great.
So, yeah, this kind of thing would be of interest to us because our planetarium shows tend to be a mix. Roughly half of them are astronomy based and half of them are terrestrial sciences. So I can definitely see applications of these techniques. One example that comes to mind is you mentioned, Kate, that you just touched on how general hydrodynamics can be modified for other applications. And you mentioned the carbon burning in stars. Could this be modified to create the sunspots?
I wouldn't say this build could, but I could definitely see people using this method in a different way to do that. I haven't actually studied stars too much or brushed up on stars in a while, but I kind of want to look into it now to see where that could possibly go.
If there's a science paper that I can find that explains how the dynamics of the surface of the star behaves, and I share that, it could be modified, this technique, or you could study the paper and see how it might be achieved.
Sure. Yeah.
Cool.
Yeah, I think it would definitely be a different build from what I got here, but for sure it's going to totally be done. Yeah.
Neat. Thank you.
Yeah, great presentation, guys.
Thank you.
Really, really cool how you guys, came up with the whole concept and everything about how to visualize it and stuff like that, and the breakdowns that you guys were giving.
Thank you. Yeah, it was fun.
Yeah, that'd be really great if you guys could, make available your the actual files, the project files, so people could study it up in case anybody wants to learn from it, and and things like that.
Yeah, not a problem.
You do that.
Cool, thank you. One more question. Your fluid sims are fairly sort of rapid, and as you know, these structures are thousands of kilometers long. So in reality,
Yes.
if you were in orbit, you wouldn't see any motion. But if you wanted some artistic license, you could have some very subtle, very slow motion. How would you go about slowing your sim down?
Well, you can do it. You can do it a couple different ways. Houdini's got this great new retime tool. I would use that probably before turning it into a cloud. So right after the fluid sim, I would use a retime there, or you could just slow down the actual sources going into the sim. But the only problem with doing it that way is that you will have way more pre-roll for your sim, or more cache space and things like that. As an artist, I'm always thinking of like the most ideal way to do it, or most quickest way to do it. So in my head, it's probably retime, but to do it more accurately, it would probably be slowing down the actual sources and creating way more pre-roll for a sim.
Mm-hmm. Although I also appreciate how quickly these things can bring your computer to its knees. And so
yes,
creating a faster sim and then retiming it makes sense.
Yes, yeah.
Are there any other questions? It doesn't have to be about the build. It could be about general questions about the science or anything like that.
Oh, one more question. How did you create looks like you had like an atmospheric haze above the planet, then you had the clouds beneath it. How did you create that sort of atmospheric haze layer?
Yes. So basically, it's more of a artistic. Okay, I don't want to say it, but it's an artistic hack that we kind of do for films. So, and for me, it was a separate layer, and I basically created a sphere, turned it into a volume, chopped about half of it off, and as its own separate layer, I created very thin density. Two atmosphere layers, almost identical. One was very thin, the other one was much thicker. The thicker one gives you the brighter glow when composited to the final render, and the other one is just to give it a nice haze over the clouds that you already see.
So is it a volume that you're rendering?
Yes.
Okay, and then
Yes.
are you using a volume shader?
Yep, just a simple volume shader, and I didn't add like a ramp to it. It's just colored the way I like, and yeah, it's just a volume shader.
Okay, thanks.
Anybody else, guys? Or you could keep throwing questions out. Feel free to answer too.
If there's no more questions, I'll leave it up to George.
Well, pretty much I was just wondering, like, how'd you guys get into, like, I guess got the whole idea to start with the presentation. So I remember talking to Kate, and she was like, "Hey, would this be cool?" And I'm like, "Of course it would be."
Well, the original idea actually came from you, because we were talking and you were like, "Oh, I'm building storm systems or something cool like that with clouds." And this was relatively, I think this was maybe late, just before April. And I think you had mentioned storms, and I was looking at planets at that time. And I was also, and I'm also really into clouds. So I thought, okay, but if I can talk about cloud and storm systems, that'd be really, really fun. But then I was like, maybe we can incorporate something else into the mix. So that's where the planet ideas and other cloud states systems came from. So that's, you kind of started, you started my idea process for brainstorming this presentation.
Oh, cool.
Yeah.
And I just like space stuff, so I joined in on it.
Nice.
Yeah.
Yeah, because it came out pretty cool. Like all the way the forms and stuff like that all over the planet. Really great.
Thanks.
Thank you. Yeah, hopefully we can show you a moving product at some point soon.
Nice. That'd be great. I guess Tim might have a question.
Cloudscape creations. Well, Kate's got her website. She's got a lot of good ideas for creating cloudscapes.
But, is this in the chat?
Yes.
Okay. I can't see the chat from my section because I'm sharing my screen, but if someone could read me the question, that'd be great.
He asked, do you have any recommendations for cloudscape creations?
Yes. So I have some resources on my site about clouds. I think I have maybe 2 or 3 pages about clouds on there. Level 80 is great. There's a lot of pages on clouds in video games, real time, films and clouds in production as well. That fluid dynamic, Nicole Sharp's fluid dynamic website is also really, really great. Again, she's been doing it she's been collecting fluid dynamic researches and cloudscape information for over 10 years. So she's got a lot in there. I highly recommend you check her out. For other cloud stuff, I think that's my main go-to resources when it comes to clouds. Other than that, CG Wiki is also really great. If you want to discover how to manipulate volumes or create cloud collisions as well.
If Tim was interested, I could screen share and show you my cheap way of making a cloud. I made it, maybe last minute, but it still kind of turned out pretty well in my opinion.
Yeah, and your method was actually really interesting when we were adding the little tiny serious cloud bands into it, because it uses a new Houdini tool from Houdini 17, which is the point velocity swap, which is really, really fun. But that was, I think, also in our build that we'll be sharing as well. So
I can show it quickly. It'll only take like a minute.
Close my screen and you
That'd be
can
great.
share your screen again.
There you go. Put this on. All right, so basically I just made this weird flat shape of a sphere, turned it into a VDB surface, and then what did I do here? Oh, that's just moving it around, simple stuff. So on the left side here, I dilated or eroded it. Sorry, didn't erode it. Dilated it, so I made it bigger. And then, sorry about if you hear a phone in the background. Turned it into a fog. So that's the beginning of our cloud shape. On the right side, I made an even bigger volume of the same shape, which you'll see in a second here. And this setup right here, it's a variation of what Stephen Nipping did in his magical volumes tutorial, I believe it's called. So I just made some alterations to something he made in the first place. So just dilated it huge, filled it with points, gave it some velocity. And the velocity, basically, you'll see in a second, it gives it the nice streaky looks for clouds. I believe we did this because Kay wanted to make serious clouds, I believe they're called.
I think so. I might be pronouncing them wrong, but yes.
Yeah. So then I just rasterized the velocity here. And down here, this cool node, VDB advect, basically, you're kind of advecting that skinny volume that I made through this velocity that I had over here. So I had some curl noise. You can see over here, this is kind of the pattern that's going through the volume, and the VDB node basically just runs this first volume through that turbulence you just saw, and you ended up getting some nice little shapes here. And this is just for my sake. I like time shifting and making sure things are moving post sim if it doesn't need to be. But yeah, this cool node basically is very useful for making quick volume shapes with noises in them. And I am cooking something. I don't know what I'm doing here. Come on. There we go. So yeah, I basically made one cloud. And over here, it's very good to use this instance node because it'll basically, if I have 200 points, 1,000 points, whatever, it'll just populate the one cloud on all these points at render time. So it doesn't have to be in your viewport being all heavy and whatnot. And I varied it up with an attribute randomizer, just gave it a different P scale and simple as that. So yeah. Check out this VDB at Vec node. It's very useful.
All right. I think Tim asked another question in the chat. So he has any tips for rendering when it comes to volumes. So I mentioned very briefly in the presentation, there are some wonderful kind of Pixar articles. Maybe we can link them in the meetup group, but they're really, really cool. Because Pixar kind of talks about how they render volumes for clouds. I apologize if you hear any noises in the background. But it's these papers are amazing, and they talk about in detail how you can do render volumetrics. But just for standard in Houdini, if you're rendering volumes, I think by default I always switch over to like either physically based rendering or micro polygon based rendering. And then from there, based on how the shader is kind of appearing with the lighting, I kind of adjust my settings from there. So if I don't need reflections, I turn them off. If I don't need refractions, I turn them off. And then I just play around with the volume step scale and everything down there on the default mantra settings. Do you want to throw in anything else, Dave?
I'd suggest not going insane with pixel samples. Keep it, relatively low. I know default's both 3x3. Personally, for my own use, I kind of just go like 4x4. And then if you're doing physically based rendering, I would use stochastic samples as well as what you mentioned with the step size and things like that, Kate. The stochastic samples is very cheap and it doesn't overly add too much render time to what you currently have.
Yeah. Don't do like 72 by 72 pixels. That would just kill the computer.
Yeah, that would crunch it down pretty bad.
Yeah.
Anybody else with any questions, if anything?
I think that's
Cool. Glad everybody liked it.
Yeah, I mean, it was great to see how you guys, got into some details on some of the stuff that you guys were working on and how you guys, but what do you, just out of the blue, in case you can talk about it, what kind of stuff are you guys more interested in doing as far as using Houdini to bring whatever visuals you would like to have in now going forward, or personal projects or anything like that?
I've been interested in pyro and explosions these days. I'm still trying to familiarize myself with the new Houdini tools, with the whole, what's it called? The sparse, all that, the new sparse stuff. I'm still like learning it. So I just want to get better at that. I know it's always changing, so it's hard to keep up, especially when you're on a project at a studio and you're kind of stuck in like previous versions of Houdini. You can't really get to the new tools yet. So other than that, that's probably where my main focus is right now.
Nice.
Yeah. I don't really know, because I think I need to do more personal projects, but I have a lot of other, I guess like tutorials and sites to uphold and add content to all the time. So I don't often get to play in Houdini. When I do, it's usually for a tutorial or something, which is cool. But one thing I really want to explore more in Houdini is chops, because I think with chops, you can manipulate waveforms and sounds and things like that very, very well. And I think everybody is well aware that a lot of things in this universe operate on waveforms or different frequencies. So I want to play around in chops more, and I think that's where a lot of my art is going to start moving towards.
Yeah, chops are fun.
Mm-hmm.
You can do like so much stuff with it. It's almost crazy that it's not even being used like for almost everything. Type of thing.
Yeah, it's almost like a niche thing that not everybody knows about.
More chops.
Anybody else have any questions or anything for Kate or Dave?
Oh, the name of the Houdini Science Discord is called Houdini Scientific Design in Houdini. There's a link in the Houdini Artists Facebook group, but I can also link it in the meetup group as well.
Nice.
Yeah. Thanks for coming out, guys. It's great having you.
Yeah, thanks for taking the time to check us out.
Thanks. Great work.
Thank you guys so much for giving the presentation. This is great. And thanks for helping us get more legit as a user group type of thing. Because last year we didn't have anything. So this year I'm trying to see if we could spec it up now that we're, on this. And thanks Side Effects for helping us present this. This is great. And everybody who came out, have a Friday night to, check out some, great visuals and stuff. So thank you guys. Thank Paola. Thank, you two guys that I know you guys are probably like, hopefully about to be relieved and have a great weekend type of thing.
Thanks.
I think we all are. Yeah.
I was like, oh man. It'd be great if, we could just hit a bar and then, just have a drink to relax. But
I agree.
This COVID thing is screwing things up.
Mm-hmm.
Hopefully this year, right? So let's see how that goes.
Yeah.
This will be a better year. I'm pretty sure about it. So, yeah.
Oh wait, somebody in the chat.
Oh, something else?
I think everybody's saying goodbye.
Yeah, pretty much everybody's like saying thank you guys for the presentation. But
thank you all for dropping by and spending time with us tonight. We really are thankful that you all came out. And
yeah.
Yes, thank you, everybody.
All right. Thanks again. Bye.